Hello class, welcome to today's lesson. Today we're going to take a look at this new concept, the concept of work in physics. Okay, now before we go into this concept, I first need to explain to you this previous concept in order to contextualize what we're going to do in a moment. So this idea is the angle between two vectors. Remember, what is a vector? A vector is any physical quantity that has magnitude and direction. For example, like displacement, if you remember. Displacement was a vector. Why? Because any particle can move a certain amount of distance in certain directions, right? For example, this particle can move this much distance in this direction, or the same distance but in another direction, or other distance in another direction. You see? So all of these arrows are representing displacements, and since displacement is a quantity that has magnitude and direction, therefore displacement is a vector. And vectors are represented often by arrows. Why by arrows? What's so important about an arrow so that they can represent the idea of vector? Well, because any arrow has magnitude, and that means the length of the arrow. It's basically its size. So it has magnitude and also a direction as depicted by the tip of the arrow, right? So that's why the arrow is the geometrical object that we use to represent a vector. What other type of vector did we talk about? Force, right? For example, if you have a box on the ground, you can push it, you can apply a force on the box in this direction, for example, or you can apply the same force but in the other direction, right? Or you can even apply the same force in other directions, for example, in inclined directions, or a smaller force in this direction, etc. So force is also a vector because it has magnitude. In other words, it has size and it has direction. Okay, good. So basically, what I want you to understand is this, guys. We're going to represent vectors by arrows, just like this, okay? All of these things for us are vectors, these arrows. Okay, now what does it mean when we talk about the angle between two vectors? Okay, very good. The idea is very simple. What is the definition? The angle between two vectors is the smallest angle made between these vectors when they are put tail to tail. So if I told you that a vector is an arrow, we can identify the tail of this vector as this part. This is the tail of the vector, and this is the head of the vector. Very simple idea. Now, if you have two vectors, let me draw vector A. I'm going to call this vector A, and I'm going to call this vector B. Okay? And when I put them tail to tail, and that means basically sliding one of them so that the tails coincide. For example, let me try to pick up B, and I'm going to slide it, keeping its direction, so that the tail of B coincides with the tail of A. So it's going to look like this. I just slided it. Try to imagine that I can grab it with my hand and I can slide it without making any rotations to the direction. If you notice, this vector points in the same direction as B. Okay, so now I have vector A and vector B put tail to tail. Can you see? Okay, so now the angle between A and B is this angle in here, and it's often represented by theta. I believe that you already know what the name of this letter because of your studies in mathematics. So this letter is a Greek letter called theta. And this is what we understand by the angle between vector A and vector B. Now, why not this other angle, guys? Because vector A and vector B also form this other angle, right? which is an obtuse angle. This is an acute angle, this is an obtuse angle. Why not this one? Why is this the correct one? Well, because of the definition. The definition is telling you that the angle between two vectors is the smallest angle that the two vectors make when they are put tail to tail. So basically, it's gotta be theta and not this other angle, because theta is the smallest one. Let me give another example. What about this, guys? Suppose you have this vector A pointing in this direction towards the right, and this vector B pointing upwards. Vector A, vector B. Let's put them tail to tail. You can either take A and slide it so that the tail of A coincides with the tail of B, or you can take vector B and slide it so that it coincides with the tail of A. It doesn't make any difference. I'm going to take A and I'm going to slide it towards B, so that now the arrangement is going to look like this. If you notice, I made the sliding of A in the same direction. You see, I did not rotate A. Okay, so we have vector A, vector B, they are put tail to tail, and therefore they make two angles in between them. They make this angle in here, this yellow angle, and they make also this red angle. Which one is the one that we're going to understand by the angle between these two vectors? The yellow angle. Why? Because this is the smallest angle between vector A and vector B. Clearly, the red angle is greater than this one. So this is the correct one. Okay, so that's how it works, guys. That is the angle between two vectors. Okay, now that we have this definition, we can start studying the concept of work. So what is work? Let's read the definition. The work done on a particle is defined as the product of the force applied on a particle, and we're going to represent that force by F, times the displacement of the particle, which we will represent by X, times the cosine of the angle between the force and the displacement. In mathematical notation, the work is equal to the force applied on the particle times the displacement of the particle times the cosine of this angle, and this angle is the angle between the force and the displacement. Now, I know what you're thinking, like what's up with this? This is very strange, and I understand you. In the moment, we will not know what work means. Like we don't have a clear idea of what it means at this moment, okay? Don't worry. I only want you to understand the formula and how it works, so that later we can give an interpretation to this concept. So far for you, this may be something like very weird. The formula makes no sense. Like, why are we multiplying the force applied on a particle times its displacement times this little thing, which is the cosine of the angle between the force and the displacement? It makes no sense at this point, and I understand you. Don't worry, you will understand what this means in the next class. For the moment, I'm just going to tell you that work is a concept that is essential in physics and that is related to energy. As a matter of fact, work and energy can be understood as the same thing. Okay, that's all I'm going to tell you for the moment. Now, what are the units of work? Work is measured in newtons times meters. Why? Why newtons times meters? Well, because work is equal to force times the displacement, and force is measured in newtons, that's why you have this, and displacement is measured in meters, that's why you have this. And as you may know by now, the cosine of an angle has no units. It's just a mathematical object. It's a number, so it has no units. So work is equal to force times displacement, therefore has units times meters. Now let's define the following, guys. In physics, in order to abbreviate, when we have 1 Newton multiplied by 1 meter, what we have done is define this quantity as 1 joule. So basically 1 joule, you can write just the J, the capital J. 1 joule is equal to 1 Newton times 1 meter. Alright, so basically this is gonna abbreviate the work. Instead of writing Newton times meter, you can just write joule and that's it, you're done. Now, let me explain to you how this formula works, guys, because as I repeat, I know that you must be very confused. Don't worry, I'm gonna show you several examples of how to use this formula in order to calculate the work done on a particle. El trabajo hecho sobre una partícula. So let's see. I'm going to show you 3 examples. And I'm going to walk you through these 3 examples very slowly. So example number 6. Why example number 6? Because example number 5 was about gravitation. And we jumped towards here. So let's see, guys. We have the following. A box is on horizontal ground. And a person pushes it to the right with a force F of 5 newtons, period. So let me stop right there, and let me actually depict what's happening. So we have the ground, and we have the box. I'm gonna draw just a very small box. And what we have in here is that some person is pushing this box to the right with a force F of 5 newtons. So let me represent that geometrically. Since I told you that forces are vectors, and I told you that vectors can be represented by an arrow, therefore let's represent this force applied on the box by an arrow. In what direction? To the right, because it's being pushed to the right. So I'm gonna begin right here, and I'm gonna draw this arrow. So this arrow represents the force F. This force F of 5 newtons. And I'm gonna write that down in order not to forget. The force is equal to 5 newtons, this force, which is being applied on the box by the person, and it's being applied towards the right. That's it, guys. This little diagram and this little writing represents all of the first statement. Can you see? Okay, next. As a result of this, the box moves to the right for 3 meters. So the box is here, it's going to move to the right, and it will end up eventually over here, right, a moment later. And therefore, the distance from here to here will be 3 meters. This is 3 meters. So far, so good. Now, find the work done by the force F on the box. Find the work done by the force F on the box. Hay el trabajo hecho por la fuerza F sobre la caja. Okay, perfect. So what do I have to do? I need to make use of the formula that I gave you here in the last slide in order to know what the work is. So the work. Oh, and by the way, you may be wondering why I'm writing these little things in here. I suggest you to do the same, guys. Like draw these things in the W, so that you make a difference between the W representing work and the W representing weight. This is for me the one that I write for work, and this is the one I write for weight. And this is capital, and this is small case. That's always a good idea. That's the reason why I do this little thing is in here. There's no other reason for that. So the formula for work is equal to the force applied on your particle times the displacement of the particle times the cosine of the angle between this force and between this displacement. So do I have the force already? Yes, it's this much, and it's pointing towards the right. Okay, now do I have the displacement? Well, yes, it's 3 meters, because that was the displacement of the box, but I also need to represent that as a vector, because the displacement is a vector. It's 3 meters also towards the right. That's just as important, guys. All of this is the displacement. Can you see? from the moment it started to move to the final point. So all of this is 3 meters. And I'm gonna write x because this is the displacement. This is the force, this is the displacement. And the displacement is 3 meters. Fine, perfect. Now what is the angle between this force and this displacement? Since they both are vectors, when you put them tail to tail, they're gonna form an angle. And since in this case both vectors point in the same direction, when you put them tail to tail, you're gonna get the following. This is F, and when you put the tail of X on the tail of F, you're gonna get kind of like a coincidence. So they're gonna be one on top of the other. And what this means, guys, is that the angle between them is 0 degrees, because they are basically pointing in the same direction. All right, so we have all the ingredients, guys. Once you get F, once you get the displacement X, 3 meters, and the angle between the force and the displacement, then you have all the ingredients to calculate the work. So let's just substitute these 3 things in here. We're gonna have 5 newtons, and then the displacement, which is 3 meters, and then the cosine of the angle between the force and the displacement, which is 0 degrees. Okay, so basically we have 5 times 3, we have 15 newtons times meters, and the cosine of 0 degrees, if you use your calculator, you will see that it's 1, equal to 1. So basically we have 15 newtons meters times 1, which in the end gives me this. The work is equal to 15 joules. Why joules? Because I told you that 1 newton times meter is equal to 1 joule. So you can change this by a J from joule. And we're done, guys. We say that the work done on this box by this force F is 15 joules. I'm going to say that in Spanish. El trabajo hecho por esta fuerza sobre la caja fue de 15 joules. And we are finished with this example. That's how it works. If you want to take a screenshot, do it. Let's move on. Example number 7. We have a little kid that is pulling a toy cart, a little cart with a cord or a handle. It's more like a handle, it's not a cord, through 3 meters. So basically this little guy is pulling the cart through 3 meters, over a distance of 3 meters over the horizontal ground, with a force of 10 newtons. The force that this kid is applying on the handle is 10 newtons. The angle between the handle and the ground is 45 degrees. So if you drew the ground, then this angle in here, the angle between the ground and the handle, is 45 degrees. Okay, and that's the whole context, guys. That's the whole context. And then they're going to ask me some things. Question A, find the work done by the force the kid applies on the cart. Okay, one suggestion, guys. When you have images like this, the best thing to do is to represent all of this in a little diagram, but in a more simplified version. Like, for example, we don't really care about the kid or the wheels of the cart or all the objects that are inside the cart, etc. We don't care about all those things. Let me tell you how you can actually abstract all of this phenomenon in a very simple diagram. What do we have? You have the ground, a horizontal ground. You have your cart, which is just a little thing. It's just a little particle, which is your cart. And basically, you have the force. I'm going to draw that in red. You have the force that the kid is applying on the cart, and that force is being directed at 45 degrees. This is 45 degrees with respect to the ground, according to this sentence, right? The angle between the handle and the ground is 45 degrees. So basically, you have a particle, you have the ground, and this particle is being we are applying a force F of 10 newtons on this particle at this angle from with respect to the ground. Now, how much is the cart moving? The cart is moving 3 meters. In what direction? Towards the left, right? Try to imagine this little kid pulling the cart. The cart will obviously move to the left. The cart will not move in this direction as the force, right? The cart's gonna move to the left. Now, let me draw that in black. So this cart is gonna move in this direction. So it's a displacement, right? And that displacement will be 3 meters according to the problem. Okay, so we have the particle, we have the force that is being applied on the particle, we have the displacement of the particle, and basically, if you notice, guys, we already have the angle between the force and the displacement, which is 45 degrees. Can you see? So we have all the ingredients. We have F, which is 10 newtons. We have the displacement X, which is 3 meters. Now, why is the displacement called X? It's just a variable, guys. Don't pay attention to that. It's often written as X, and that's it. Don't worry about that. And the angle between the force and the displacement is 45 degrees according to this diagram. And once I have this and this and this, I can calculate the work. The work is going to be force times displacement times the cosine of the angle between force and displacement. And that's it, right? I just put those things in here. 10 newtons times 3 meters times the cosine of 45 degrees. And I just calculate all of this thing in the calculator. So grab your calculator. I'm going to grab mine and calculate all of that stuff. You're going to get 15.759 joules. Once again, why joules? Because it's not 1 joule is a newton times a meter. So this is what you have. So this solves the question A, guys. Fine. This is the work done on the little cart by the force that the kid is applying on the cart. Okay. Now I'm gonna erase all of this now because we have another question. If you look at question B, question B is asking me, find the work done by the force applied by the ground on the cart. I'm going to repeat. Find the work done by the force applied by the ground on the cart. Why am I saying this? Well, because if you notice, guys, the cart is being subjected to not only this force that the kid is applying, but it's also being subjected to other forces. For example, the one obvious one, this little cart is being subjected to the force of gravitation, which is its weight, right? Remember that that's the weight of the object, and that's the force that the Earth, the planet Earth, is applying on this object towards its center, right? So we have the weight of the cart. And what other force is being applied on this object? Well, the ground is obviously applying a force in the opposite direction. Okay? In this direction, the ground. So this other force, let me call it Fg, force applied by the ground on the cart. This is the one that I'm interested in. I can't forget about the weight. And this force is applied vertically. So basically, guys, this is the force that the ground applies. Let me try to do it more vertical. There you go. This is the force that the ground applies. By the way, don't confuse this with gravitation. What I mean by this is ground. The force that the ground is applying on the cart is being directed vertically upwards. Okay, so what could be the work done, guys, by this force on the cart? Do we actually need this force? Because we don't know it, right? They don't tell me what this force is. But do we really need it? We don't. Let me tell you why. If we wanted to calculate the work done by this force on the cart, all you need to do is multiply that force, the force applied by the ground on the cart, times the displacement, which is 3 meters, times the cosine of the angle between this force and this displacement. You see? And by the way, let me erase, in order to make this cleaner, let me erase this other force, because we're no longer talking about this other force. So let's erase it. Let's erase all of this. Let's clean some of the problem. Okay, so basically, we have this force, this displacement. This is the force that the ground applies on the cart, and therefore we also have the angle, this angle between this force and this displacement. Now tell me what this angle is, guys. If this force is being directed upwards, and if this displacement is being directed to the left, then what angle should this be? This angle should be 90 degrees, right? Because these two vectors are perpendicular. So theta is 90 degrees. And let me introduce that in here. And you're going to see why. This is FG. We don't know it yet. X is 3 meters. And theta is 90 degrees. Now, I told you that we don't really have to know this force. Why? Because take your calculator and calculate this number, cosine of 90 degrees. Do it, and you will get 0. This number is 0, guys. Cosine of 90 degrees is 0. So it doesn't matter what value this force is. Ultimately, all of this will be 0, because whatever this value is, times 3 times 0 will be 0. Can you see? So the work done by this force on this particle will be 0 joules, regardless of what value this is. We don't really need it. That's what I'm trying to tell you. So the work done by the force applied on the cart by the ground, that work is going to be 0 joules. Okay, and that solves example number 7. Now the example number 8, let's solve it live, this one. Okay, so let's stop the lesson right there, guys, and we're gonna work through this example in a moment with me. So that's it, guys. Thank you so much.